Okay, the next chapter is chemical equilibrium. Now, first things first, this really should be chapter 14. Um, if I compare what we should expect in this chapter to what we have already seen in chapter 13. Recall in chapter 13 we talked about how fast the reaction could occur. So we discussed the speed of the reaction, the kinetics of the reaction, activation energy, what it requires, so energy and orientation for the product to form, presence or absence of catalyst, how that affects the reaction. In this particular chapter, we are going to actually examine how far a chemical reaction goes. So, the speed of the chemical reaction, in other words, is determined by the kinetics, whereas the extent of the reaction, how far has it occurred, how much of the products are present, how much of the reactants are present. So, the extent of the chemical reaction is determined by thermodynamics. And in this particular chapter, we are going to discuss this measurable quantity called as chemical equilibrium constant as we go along. So, chemical equilibrium will examine the extent of reaction, whether the reaction has gone up to 70%, 80%, or what. And based on that, you would then be able to make a call whether a certain reaction is going to hardly form any products, or is it going to completely convert into the product. So one can, I guess, you can say that the success of the reaction is going to be dependent on the kind of equilibrium constant that we are going to get. Chapter 15 and 15, 16, and 17 will further take this chemical equilibrium into aqueous equilibria. But in this chapter, it's the basics. We are going to get you started into what equilibrium is all about. All right, so like I said, we are going to discuss how far a reaction proceeds towards completion before it reaches a state of chemical equilibrium. So what exactly happens at equilibrium? That's what we are going to discuss. Now, at equilibrium, when equilibrium is achieved, the concentration of the reactants and products, it sort of remains constant. That means you don't no longer see a change in concentration of the reactants and products. What do I mean by that? I want you to recall the little kinetics curve that we drew in chapter 13, where we plotted concentration against time, and we said the slope is really steep in the beginning and then it kind of flattens out. And we said that this is for reactants because the concentration of the reactants decreases as the time increases. Likewise, if you wanted to plot the products, it's going to look something like this. But realize, past a certain point of time, perhaps here, essentially there is no more change in concentration. And this is the part where chemical equilibrium has been achieved, has been reached. So this is a state at which one can say that the concentration of reactants and products no longer changes. So one might assume that an equilibrium or achieving an equilibrium means that you have achieved, the reaction kind of stops because the concentrations are not changing. In reality, however, what happens is that there is a forward reaction. So let's say A moles of A react with B moles of B, giving you C moles of C and D moles of D. There is a reaction that's forward, and there is a backward reaction that gets kicked off, where C moles of C react with D moles of D, giving you A of A and B of B. And so if the speed with which the forward reaction and the backward reaction take place, if that speed becomes exactly the same, hopefully you can see that there won't be any further change in the concentration of the reactants or the products, and hence it would achieve this constancy, and hence we would say that equilibrium has been achieved. So what do you expect in an equilibrium mixture? You should expect a mixture of reactants as well as products in an equilibrium state. Now, you might ask, why are we interested in determining the extent of the reaction? And the answer to that kind of goes back to the fact that what is the relationship essentially that exists between the concentration of the reactants and the product. So understanding equilibrium, you would be able to understand that. You would be able to mathematically derive the equilibrium concentrations from the initial concentrations, and you would be able to tweak reaction conditions. So if you're seeing that your reaction is getting stuck in an equilibrium loop, you can perhaps change the reaction conditions and you can force the reaction in a direction that you want it to take. So you would be able to tweak the reaction conditions for a better yield of the product. So for instance, let's say you have an endothermic reaction which requires heat, and if you're not providing enough heat, then the reaction is going to, kind of look as if it's static. On the other hand, if you want to push the reaction more towards the products, you might have to increase the temperature. So those kind of decisions can be made, they can be brought about by understanding where exactly the equilibrium lies for a certain reaction. Now, just to give you a flavor of, equilibrium reactions, of course, they occur around us all the time. But if you've ever wondered how does fetus in the mom's womb, how are they able to get oxygen? Realize we know that hemoglobin is the carrier protein which essentially picks up oxygen, and it's in equilibrium. And it's a good thing that it's in equilibrium, because if the binding of oxygen and hemoglobin would be very, very strong, then hemoglobin would want to take up oxygen but never want to unload it. And we don't want that. We want it to be able to pick up the oxygen and when the time comes also be able to unload it. So having this equilibrium, which is shown as the forward and the backward, is a good thing. Now, if you think about the way adults breathe, the way you and I breathe, essentially you would be like, okay, yeah, we breathe, and then the oxygen diffuses through the lungs, and then it's picked up by the hemoglobin, and then it's carried to the tissue, and that's where it's unloaded. But realize that a fetus has essentially its own circulatory system, and so the mother's blood never actually flows into the fetus's body, and the fetus cannot get any air in the womb. So the question is, how does the fetus get that oxygen? And the answer lies in the properties of the fetal hemoglobin, which is slightly different than the hemoglobin for adults. So I'm just going to write that as HbF for fetus. And of course, there is an equilibrium between the fetal hemoglobin. So that does pick up the oxygen, give you HbFO2. However, the equilibrium constant, so equilibrium constant for the fetal hemoglobin is larger as compared to the adult hemoglobin. So the way this works is essentially at the placenta, the adult hemoglobin comes in with the oxygen and it unloads the oxygen. So here is my fetus, and here is mom. And the fetal hemoglobin will then pick up that oxygen, the oxygen that was unloaded, and HbFO2 will be obtained, and then it is going to carry it into the fetus, and that's where it's going to unload it. So you can think that it's kind of like a transfer that's occurring from the mom to the fetus, and the reason why we are able to do that is because the affinity of oxygen for the fetal hemoglobin is slightly larger as compared to that of the adult hemoglobin. And so the forward reaction in that case is allowed, and that is the reason why it would take place. Now, in GenChem 1, as well as in the previous chapters, we have basically generally always assumed that as chemical reactions proceed, they cause a complete conversion of reactants to products. What I mean by that is, let's say you have, let's consider maybe a reaction like a precipitation reaction. Okay, so you have KNO3, or rather, whoa. Let's not KNO3. Let's use Ki plus PbNO3 twice, and we are forming PbI2 plus KNO3. KNO3 is my product. Okay, I need two of these. So the fact that it's a precipitation reaction, we say that once the precipitate is formed, boom, there you go, your product is formed, and it's 100% conversion of the reactants into the products. In reality, however, many reactions do not even go to completion, and they remain in this dynamic state of equilibrium. As an example that I have here, I have dinitrogen tetroxide, which is getting converted to 2NO2. So I'm showing you here that the dimer essentially goes through bond cleavage between the two nitrogens, and 2NO2 molecules are formed. Now, if you follow the concentration versus time, this reaction, you can see that if the concentrations are really tiny, then perhaps the two curves won't even cross over. However, if the concentration is increased, essentially you will see for the backward reaction, you will see 2NO2 giving you N2O4. As you increase the concentration, so we increase the concentration, more and more NO2 is going to essentially get converted into N2O4. Now, how can we visually see this? Turns out that NO2 is actually a red-brown gas. This is a red-brown gas. And N2O4 is colorless. So when you are running the reaction, there is a forward reaction where N2O4 or NO2 gets converted into N2O4. There is a backward reaction where N2O4 is giving you NO2 back. And the reaction kind of stays in this equilibrium. So at any given point of time, that red-brown color doesn't quite completely go away. And notice again, this region of constancy as far as the concentration goes, which basically tells you that the rate of the forward reaction, so rate of forward reaction is equal to rate of backward reaction. So for this case, one can say that rate of forward reaction, so I'm going to, the way I have written, I would say rate of forward reaction is going to be Kf NO2, and if you consider that the elementary step, the way we did in the last chapter, we would be able to say that this is equal to Kb, and in this case the reactant becomes N2O4, and of course there is no power in that case. And so if rate forward is equal to rate backward, we could say that Kf over Kb is equal to N2O4 divided by NO2 squared. And turns out that this ratio of the forward over the backward reaction is given a name. It's called the equilibrium constant. I'll discuss that in a little bit more detail, but I want you to realize a couple things here. First things first, it seems like as the concentration of the reactant and the product doesn't change, that means the reaction has stopped. but that's not quite true. It has just gotten in this loop of chemical equilibrium where the rate of forward reaction is equal to rate of backward reaction, and so it almost seems like the concentration becomes constant. So in that sense, it is a dynamic, it is a continuous process, it is a dynamic process. And then hopefully you were also able to see that the ratio of the concentration of the products divided by the ratio of the concentration of the reactants, it can be given as the rate constants of the forward and the backward reactions, the ratio of that, and that has a specific name called as equilibrium constant. So again, realize that the reaction will be considered reversible, which is why we are using the double-headed arrow for the forward and the backward. Now, sometimes you might see an arrowhead, a double-headed arrowhead like that, but if you're writing yourself, this is probably a better way of writing. But realize either way, it's not a single arrow pointing towards the products. So that's what's most important. Even if you had a precipitation reaction, a lot of times you might see an equilibrium like that, and that basically tells you that this particular equilibrium lies more towards the product than towards the reactants. That means the backward reaction is not as predominant as the forward reaction. So that's what it means. But realize that all reactions are reversible, and all reactions are reversible, and there will be a forward and a backward associated with every single reaction in question. Okay, now, for all practical purposes, the example I gave you a couple minutes ago where we were forming lead iodide and KNO3 from PbNO3 twice and Ki, two of those. We call those kind of reactions somewhat irreversible because at the end of the day, as you're ready to isolate your product, the equilibrium mixture contains almost all products and no reactants. So the reactants that are available are so little in amount that you would call that like traces. So that's when you would say that you can write down the reversible equilibrium like that. So in reality, the reverse reaction in that case will be too slow to be detected, but it still is a reversible reaction. So the reaction does not stop at equilibrium. Again, realize it's just that the concentrations are not changing because the rate of the forward reaction is now equal to the rate of the backward reaction. So if you are still thinking, but what does equilibrium mean in physical terms? Let me give you an example for that. You can consider a soda can, okay, which has a liquid, so Pepsi, Coke, whatever, and it's a carbonated drink, so there is CO2 right on top of it. Now, at any given point of time when it is unopened, there is essentially a dynamic equilibrium that exists between that little area and the liquid that you have. And realize that the molecules of dissolved CO2 will constantly leave the liquid and they will enter the gas phase, while CO2 molecules will leave the gas phase and dissolve in the liquid. So at any given temperature and pressure, these two opposing processes are in balance. What happens when you open? So you have that little lever and you open that. So at this point of time, the balance is disrupted and some of the CO2 gas above the soda surface escapes into the air. Because the pressure is suddenly reduced. And so immediately you would see that the soda would start fizzing and bubbles of CO2 will form. Why? Because these bubbles are going to form because the solubility of the gas in the liquid is proportional to the partial pressure. We discussed that previously. And so since the partial pressure is going to decrease, more and more CO2 is going to escape. And if you just allow it to happen over a period of time, that soda goes flat. Another way to sort of explain this would be if you consider perhaps like a subway train. All right, so we are in station A, and maybe this particular car can carry total of 50 people. All right, and so the door opened, 10 people got out, and 10 people got in, right? So realize that now, as the train moves, essentially the total number of people that are present within the system is still the same. However, the faces have changed, right? So that's happening in case of an equilibrium also. As the reaction proceeds, two molecules are going to collide with each other, and they're going to hopefully try to go up the energy barrier and form the products. But they are going to be different at every given point of time because there is a backward reaction that's also triggered off. So consider people analogous to molecules here. As I was telling you, the chemical equilibrium is a dynamic state. It is the state at which the forward reaction and the backward reaction rates, they are going to become equal. So the Kf, so it's not the Kf and but the Kf times whatever the concentration of the reactants will be equal to Kb times the products, right? And so these are going to basically become equal. So in a sense, there will be no net conversion of reactants and products. So over here, I'm showing you the rate of forward reaction, rate of the reverse reaction, and they are essentially matching up. And that is the state we say is chemical equilibrium has been achieved. All right. So let's take a look at a question. The question is, which of the following is correct? Some reactions are truly not reversible. All reactants go to all products in all reactions. I don't know what that means. All reactions are reversible to some extent. That sounds good. The rates of the forward and reverse reactions will never be equal. That's not right because we just talked about that when dynamic chemical equilibrium is hit, essentially the rate of forward and reverse reaction does become equal. So choice number C is the appropriate answer. All right, so let's take a look how we can measure equilibrium. Like I was saying earlier, equilibrium can be measured using what is called as the equilibrium constant. Now, in the next 4 chapters, we are going to go over at least 9 or 10 different kind of Ks. So this is the first one of them. And I'm going to call it Kc because it's based on concentration. So let's say you have a generic reaction where A moles of A react with B moles of B to give you C moles of D and D moles of D. And so for that equilibrium reaction, so notice I'm using the double-headed arrow, according to what is called as the law of mass action. Law of mass action. The product of the concentrations of the products raised to the power of the stoichiometric coefficient divided by the product of the reactants raised to the power of their stoichiometric coefficient, that is going to be the constant, equilibrium constant, Kc. This is similar to what I just talked about in the last 2 or 3 slides with a specific example of N2O4 and NO2. Couple things that you should realize here. The equilibrium equation must be in gases or in ions. So the subscript here should be either a G or it should be an AQ for these to be able to participate in the equilibrium constant. Solids and liquids do not participate in the reaction, and the reason for that is that the concentration of pure solids and pure liquids remains nearly constant. It doesn't change, and so essentially we don't use those in the equilibrium equation. Also realize that we usually do not use any units, so no units for equilibrium constant. However, we do specify the temperature at which the equilibrium was studied. So very often you would see K was found to be equal to blah blah at 100 Kelvin or maybe 600 Kelvin and the likes of those. Now the question is, what does Kc mean? Realize Kc is a ratio of concentration over concentration. It's concentration of products over concentration of the reactants. So if your products are high, that means the forward reaction is more predominant. That means this numerator is a larger number. That would mean that the Kc is also a large number. It's a large value. So that would automatically mean that the forward reaction is more predominant as compared to the backward reaction. On the other hand, if the concentration of the reactants is more, then the value of Kc will go down because the denominator will be higher, and so the backward reaction will be more predominant as compared to the forward reaction. Realize for any equilibrium to hit in the beginning, as the reaction begins, your reactants, so in this case your A and B are going to react very vigorously, and they will start generating some amount of C and some amount of D. And only when C and D will get formed can you expect that they are going to react with each other and start forming A and B back. So that backward reaction is going to kick in only once there is an appreciable amount of C and D in the system. So as you can see, I wrote the general reaction, and according to the law of mass action, I can see that the products of the concentration of products raised to the power of their stoichiometric coefficients divided by the product of the concentration of reactants, that gives me the value of Kc. For the reverse reaction, which means C moles of C plus D moles of D giving A of A and B of B, you would get a Kc prime, which is for the backward reaction. And if you compare the two, hopefully you can see that one is the reciprocal of the other. What does that tell you? That tells you that if you knew the equilibrium constant for the forward reaction, then that will be equal to 1 over equilibrium for the backward reaction. So for any reaction, it will be very easy for you to determine the equilibrium constants for the backward reaction or the forward reaction, depending on the data that is provided to you. So the question is, write the equilibrium equation for each of the following reactions, and the equation is given, so hopefully you can see that equilibrium constant can be written as concentration of the products. There's only one, which is ammonia raised to the power of 2. You must always make sure that it's a balanced equation. In this case, it is 3 times 2 for hydrogens, 2 times 3 for hydrogens, 2 nitrogen on both sides. But it's always a good idea to make sure that you do have a balanced equation. H2 raised to the power of 3. That will be the equilibrium constant for the first one, and the equilibrium constant for the really is the backward reaction of the first one. It's going to look like N2 H2 raised to the power of 3 ammonia raised to the power of 2. Okay, the question is, oxidation of sulfur dioxide to give sulfur trioxide is an important step in the industrial process for synthesis of sulfuric acid. Write the equilibrium equation for each of the following, and you have to determine the equilibrium constant for both of these. So realize these are inverse of each other. There's 2 ways to go about it. You can determine A and then figure out B, like independently. Alternatively, you can determine A and then say that since B is just the inverse of that, so 1 over that number is going to give you the value for B. So let's take a look. For A, you can safely say SO3 square of that divided by SO2 square of that and oxygen. That's the way you would write your equilibrium constant. And now I'm going to plug in the numbers for this case. So that's going to come out to be 5.0 times 10 to the power of -2 square of that, and then 3.0 times 10 to the -3, and 3.5 times 10 to the negative 3. And so this will be 25 times 10 to the negative 4. And you can punch in directly. I'm just showing all steps. And when I plug in the numbers, I'm getting 2.38 times 10 to the power of 2. And if you wanted to determine the value for B, you can just go, since that's going to be SO2 square of that times oxygen divided by SO3 square of that. You can plug in the numbers, or you can simply just take 1 divided by the number that you had obtained. So 1 divided by 238, and that will give you the value of the backward reaction as well. So let's do that. And that comes out to be 0.0042 as your overall Kb value. So again, to really discuss the significance of the equilibrium constant very quick, since we know now how to express the equilibrium constant, realize for any reaction, let's say I have H2 gas plus Br2, that's also in gas phase, in equilibrium with 2HBr, and the K value for this is given as 1.9 times 10 to the power of 19 at 25 degrees Celsius. Okay, what does that tell you? What does that mean? Realize that this equilibrium constant is extremely large. It's way more than 1. And so that means that the numerator in this case, which specifies the amount of the product over the denominator, which specifies the amount of reactants, essentially, since numerator is gigantic, that means the forward reaction is favored. Forward reaction favored. If your K value would have been much less than 1, and so an example of that would be, let's say you have N2 plus O2 giving you 2NO. K value for that is 4.1 times 10 to the power of negative 11 at 25 degrees Celsius. So this is an example where you have such a small number for the equilibrium constant. So the backward reaction would be more predominant. And if you have K equal to 1, then you can say that neither direction is favored and the forward reaction basically proceeded about halfway through. Halfway through. Okay? And essentially one could say that any number more than 1,000 is going to be considered a larger value than 1. Any number less than 0.001 will be considered a small number. Any number in between is going to be considered where both reactants as well as the products are going to be present in that reaction system. All right? Another thing that I wanted to discuss, of course, I gave you the inverse of an equation, the reverse of an equation, which basically means that the forward and the backward are going to be reciprocal of each other. But what would happen if you multiply the coefficients of the equation by a certain factor? Then how does the equilibrium gets affected? So for instance, if you have a general equation a plus 2b giving you 3c, and your K can be written as c raised to the power of 3 a times b raised to the power of 2, and let's say I'm multiplying this equation, the whole thing, by some number n, okay, and I'll define n later. So n moles of A plus 2 n moles of B giving you 3 n moles of C. What that means that the K is now going to be written as C raised to the power of 3n, A raised to the power of n, B raised to the power of 2n. Or you can simply say that it is C raised to the power of 3 divided by A times b squared whole raised to the power of n. But what was c cube over ab square? It was k. So this new k, let's just call it maybe k prime to differentiate, that's going to be k raised to the power of n. So just keep that in mind. Likewise, if you add two or more individual chemical equations, then the equilibrium constants, they get multiplied. On the other hand, if you subtract, then the equilibrium constants, they get divided. And we'll take a look at, when the time comes, we'll take a look at that as well. So far we have written the equilibrium constant in terms of concentration of reactants and products. Anytime you have gaseous mixtures, and so you have some idea about the partial pressure of a particular gas, since that partial pressure is proportional to the concentration, you can even write down the equilibrium constant in terms of pressures. In this case, though, you're going to use a different denotation, so you would call it Kp. So let's say you have a generic equation: A moles of A react with B moles of B, giving you C moles of C and D of D. You can write the Kc as C raised to the power of C times D raised to the power of D divided by A raised to the power of A and B raised to the power of B, right? And since, like I said, the concentration of any material is related to the partial pressure, you can say that it's the number of moles, it's a molar concentration, so it's the number of moles of that particular material. So for C, let's say, it's going to be number of moles of C divided by the volume. And if this is gas, then it should follow the ideal gas equation. So you can say that the pressure due to C times volume is equal to the number of moles of C times RT. So you can say that pressure is going to be NC RT over V, which, by the way, is the concentration that we are talking about. So the partial pressure is nothing but molar concentration of C times RT. So you can, if you wanted to, you could essentially plug in, write down the concentrations in terms of partial pressure. So you could say that C would be equal to PC, partial pressure due to C, divided by RT. And if I do that, then my K C would start looking like PC over RT raised to the power of C, PD over RT raised to the power of D divided by PA over RT raised to the power of A and PB over RT raised to the power of B. And if that's true, then you can simply write that as PC raised to the power of C times PD raised to the power of D divided by PA raised to the power of A and PB raised to the power of B. And the 1 over RT is going to look like C plus D for the numerator, and you have 1 over RT A plus B as the denominator. And that can be written again as, and let me fix that, or let's just continue to show all the steps. That can be written as PC raised to the power of C times PD raised to the power of D divided by PA raised to the power of A, PB raised to the power of B, and we have 1 over RT C plus D minus A plus B. Notice these are the number of moles of the products and these are the number of moles of the reactants. So one can say that this is the change in number of moles. change in number of moles. So this guy, the partial pressures, that has been given a constant Kp, and this is 1 over RT delta N, which is the change in number of moles, or one can say that Kp is equal to Kc times RT raised to the power of delta N, where delta N is the change in the number of moles, R is the gas constant 0.08206, T is the temperature in Kelvin, Kc could be your equilibrium constant. So if that is given, you can simply use that to determine the value of Kp for that particular situation. Now there are certain situations where you would find that the value of Kp and the value of Kc would be exactly the same. And what would those be? If delta N turns out to be 0. So if the number of moles of the reactants and the products doesn't change, then delta N is going to be 0, and you can say that RT raised to the power of 0 is going to be equal to 1, and in that event you can say that Kp and Kc are going to be exactly the same. So there's a question here: in the industrial synthesis of hydrogen, mixtures of CO2 and H2 is enriched in H2 by allowing CO to react with steam. So that's the water gas shift reaction. The value of Kp is required at 700 Kelvin if the partial pressures are given. So it's pretty straightforward. Kp is what we seek. So if I know the pressure of CO2, if I know the pressure of hydrogen, this is a balanced equation, divided by pressure of CO and pressure of H2O, I will have my answer. So partial pressure of CO2 is 6.12 times H2 is 20.3 divided by 1.31 for CO and 10.0 for H2O. Realize all of these contain 3 sig figs, so we are going to get our final answer in 3 sig figs as well. So I'm going to just punch in the value on my calculator, and the answer comes out to be 9.48 is the value of Kp that we obtain. All right, next question. The question asks what I actually already discussed. When is it that Kc and Kp would be equal? And I told you that provided you're seeking all the numbers of all the reactants and the products that are going to participate, that means you have to look for gases and aqueous only. So in this case gases, since it's Kp that's involved. If the number of moles of the products is equal to the number of moles of the reactant, you would say that it will be equal. So the answer is B. Okay, let's take a look at another one. The question is, nitric oxide reacts with oxygen to give nitrogen dioxide. Important reaction in the Ostwald process of nitric acid. So you're given Kc, and you have to determine Kp at 227. So it's a pretty straightforward question. You know the relationship that Kp is equal to Kc RT raised to the power of delta N. First, make sure that it's a balanced equation, and looks like it is. Kc is given to be 6.9 times 10 to the power of 5. R is 0.08206. You will need to convert the 227 into Kelvin by adding 273. So sounds like that's going to be 500 Kelvin. So I'm going to put in 500. You have 2 moles of the products, you have 3 moles of the reactant, so delta N is going to be -1. And just simply solve it now. Now, one thing I would like to say is whenever you have a power of -1, that basically means that it's 1 over that. So x to the power of raised to the power of -1 means that you're talking about 1 over x. So that's what I have done here, that the product of 500 and 8206, that came out to be 41.03. So I basically put that in the denominator to figure out the overall value of Kp. You could, if you wanted to, you could actually even do logs for this case and go with that. If you're more comfortable, with that idea, you can always use logs and then take it out of the log and get your answer that way. All right, there's another question that I have here. Kp is equal to 1.3 times 10 to the negative 2 at 1,000 Kelvin. What is the value of Kc? So Kp is given now as 1.3 times 10 to the negative what? 2. Let me change the color just so that I can see it's a different question. R is still 0.08206. I'm just showing you which numbers are going to be plugged in where. It still is going to be negative 1, you know, and we will now determine the value of Kc. So that will look like 1.3 times 10 to the power of negative 2. And we are going to put in the 820, or rather 82.06 in the denominator and solve. So I'm going to get a final answer of, and it comes out to be 1.066 as the final answer.